Okay, hope you enjoyed the musical introduction. So we're going to look a little bit today at a topic that's important for calculus, actually, known as average rate of change. When you take calculus, you learn a lot about this, and also a concept called instantaneous rate of change. So average rate of change, what it really is it's just basically the slope of a line that goes through 2 points on a curve. So you've got your slope formula that you've learned before, change in output, change of input. It's a ratio of change in y over change of x. Okay, so average rate of change, we're going to start just learning the concept like this. So if you have a graph, you have a function like you do here. We have two x values. We have x equals -4. So that gives us point -40. And then we have x equals -1, which on the curve, it looks like that point is -1, 3. So when you're doing an average rate of change, what you're doing is all you're doing is finding the slope of this line. Okay? And what you'll find is as the points change on the curve, the average rate of change will begin to change. So I'm going to abbreviate this AROC, the formula delta y over delta x. What you're really doing is you're doing the function value of one of the x values minus the function value of the other y value. Then you're doing the change of x, and you're doing this in the same order. And that's no different than just saying y2 minus y1 over x2 minus x1. Okay, so if we do that, f of -1 is going to be 3, f of -4 is going to be 0. So we're going to do 3 minus 0. Then we do the x's, and we have to do the subtraction in the same order. You can't mix up the order. So you have -1 subtract -4, like that. So we're going to have 3 over -1 plus 4, which is 3 over 3. So that gives an average rate of change of 1. And really all that means is if you look at your graph, if you have a slope that's 1 over 1, it means that you're doing a rise of 1 and you're doing a run of 1, which just means you're going up and to the right. So notice on here that all I'm doing is just going up 1, right 1, up 1, right 1, up 1, right 1, and you're always going to be on that line. So you could even do the average rate of change just by counting out the slope. Okay. Next problem. Again, I'm giving you two different x values. So on this one, x equals 0. That appears to give you the point 0, 600. X equals 40. That appears to give you the point 40 and 200. Again, these every notch on there is going up 200. So again, what you're doing is you're finding the slope of the line that goes through those 2 points. So when we do this, the average rate of change, again, what we're going to do is f of 40 minus f of 0 over 40 minus 0. Now be sure you do those things in the same order. You could also do f of 0 minus f of 40 as long as you do 0 minus 40. You're going to get the same answer regardless of which way you do that. So if I take the function values and subtract those, I'm going to get 200 minus 600. And then 40 minus 0, if I subtract the x's to get the change in x, that'll give me 40. So this looks like that's -400 over 40. You could divide that out and you get -10. So the average rate of change on this is -10. Notice if you did this backwards, you would do, if you did f of 0 minus f of 40, you would have 600 minus 200. If you did 0 minus 40, you'd have -40. So you're still going to get exactly the same answer. So it doesn't matter which way that you do that. So that's how you find average rate of change. Okay, so on this next page, I'll have you just do 2 problems. Go ahead and pause the video. And then when you're ready to check your work, just resume the video. Okay, so here's the answers you should have come up with. Again, the 2 points on here are the 0.23 and 57. So I'm doing the slope formula to get 2. And on number 2, the 2 points are 0.255 and 1, 2. So I do the slope to get -4. Pause the video if you need to study over that or if you made any mistakes. Okay. Then we'll go to the next thing. We're looking at a rate of change if you're given a function this time. So if we go down to this example, what's different about this is I'm giving you a function. I'm not giving you a graph. So you still essentially do the same thing. So what I'm going to do on this is we're going to go ahead and we need to find two things. We need to find f of 0. So we just plug in and do 3 times 0 minus 5, which gives me -5. So that gives me a point 0, -5. Second thing you want to do is you want to do f of 4. So we do 3 times 4 minus 5. Work that out. That will be 12 minus 5. So that will be equal to 7. So that gives you another point, which is the 0.47. So now when you find the average rate of change, you're going to do, it's up to you which order you do this in. I'm going to do f of 7 minus f of -5. Nope, that's not right, teacher. You're thinking ahead here. So you want to do f of 4 minus f of 0. Okay, we got to do the function values. And then we divide by the change in x like that. Again, you could go backwards and go f of 0 minus f of 4, as long as you do the change of x as 0 minus 4. Okay, so now if we do this, f of 4, we found out that that was 7. F of 0, we found out that was -5. So we just work out 7 subtract -5. 4 minus 0 gives you 4. So this would be 12 over 4. That would give you an average rate of change of 3. Okay. So if you were to interpret what this graph looks like, you have the function f of x equals 3x minus 5. From your background, hopefully you remember mx plus b is the standard form of a line. So you have a y-intercept of -5. Okay, so that just means we would go down and put the point 0, -5 on there. And then your slope is 3. You can always put a whole number over 1. And remember, you're doing change in y over change in x for a slope. So you're really going up 3 because that's a positive number. And you're going to the right 1 because that's a positive number. So if you do this, you go up 3 over 1, up 3 over 1. And essentially what you're doing is finding the slope of the line. So on this problem, you could have got that answer 3 just by looking at the slope of the line. So if you have a line, the average rate of change is the slope regardless of which 2 points you are. So this average rate of change will always be 3 on this line. It's never going to change. Okay, next problem. We'll do this like this. So kind of do the same thing. We need to start by doing f of -1. Plug it in. We got 4 minus -1 to the second. So that's 4 minus 1. That's equal to 3. That gives you a point -1,3. Take the second x value and evaluate it. So we need to find f of 3. So we do 4 minus 3 to the second. That's 4 minus 9, so that's -5. So you get a second point, which is 3, -5. Okay, so it's all about finding 2 points. Then the average rate of change, you want to do the change in y over the change in x. Change of y, you're going to do, and it's up to you which order you do this in. I'm going to go f of 3 minus f of -1. And then I'm going to do the change in x by doing 3 minus -1. If you're finding a change, you're subtracting to find how far apart two numbers are. So basically, let's see, f of 3 was -5. F of -1 was 3. So we'll do -5 minus 3 over 3 plus 1. So that's -8 over 4. That average rate of change is going to be -2. Okay. Now, just to do a graph, and you could do this with a calculator, I'm going to bypass that though and just make a table of values. So let's pick some x values. Let's just pick 0, 1, and 2, -1 and -2, and then let's get a good graph on here. And I guess we should also go all the way up to 3. So if I work this out, I'd have like 4 minus 0 squared would be 4. 4 minus 1 squared would be 3. 4 minus 2 squared would be 0. And then 4 minus 3 squared would be -5. I know I'm doing that fast, but you can take the time to calculate those things out carefully if you need to. If you go here, 4 minus -1 squared would be 4 minus 1, so that would be 3. And then 4 minus -2 squared would be 4 minus 4, so that would be 0. So I'm going to plot these points. We have -2, 0, -1, -3. No. I'm plotting that in the wrong place. Crap. So -1, 3, 0, 4, 1, 3, 2, 0, and then 3, -5. So you have a parabola. It's a quadratic function. So the mathematical meaning of this problem is you have 2 points. You have this point -1, 3. And you have this point 3, -5. So see, all you're really doing is just finding the slope of the line that connects those 2 dots. And since our answer was -2, that just means we're going to go down 2 and to the right 1. So if I do this, notice what happens. I go down 2, right 1, down 2, right 1, down 2, right 1, and that will follow that slope and get you from the first point to the second point. Okay, so you don't have to graph to do these. It's just a matter of finding 2 points and finding the slope. Okay, remember to pause the video anytime you need to. I'm going to go ahead and move to these 2 problems. I'm going to pause the video, see if you can do these okay. And as soon as you resume the video, you can pause and check your answers. Okay, so first one you should have got -1. Second one you should have got 3. You can do these graphs on a graphing calculator if you want to. Just to get a good sketch on this, that's what I did. You could also do a table of values if you wanted to. But ultimately, on these 2 problems, you want to check that you had 2 points on this first one. These are the 2 points. And then when you do your slope, you're doing -6 minus -2.5 over 3 minus -0.5. You also could have done that backwards and done -2.5 minus -6 over -0.5 minus 3. It'd give you the same answer. Second problem, your points were -1, -4, and 3, 8. Okay, find the slope on that. You would do that calculation to get 3. Okay, so pause, and if you made any mistakes, just make sure you learn from your mistakes. And that's the 3-step process on average rate of change. Okay, next thing on here is something that's preliminary to calculus. In a calculus class, you tend to learn how to work with what's called a derivative of a function to identify where a function increases and decreases. In this class, we're just going to get comfortable with what the concept is. So really, a function's increasing on an interval when the y values get bigger. And we're measuring this from left to right. So if the y values are getting bigger on that interval, then we say we're increasing. We're decreasing on an interval if the y values are getting smaller. Again, we're going left to right. We say it's constant if the y values do not change, if they're always the same. So if you look at this graph right here, this region here would be constant. We would say from -infinity to -5. Okay, we're always naming these intervals with x values. So from negative infinity until we get to -5, your constant. Then we're decreasing. That looks like from -5 to -1. Then it decreases again from 3 to infinity. And then you're increasing from -1 to 3. So when you're constant, the y values are the same. When you're decreasing, the y values are getting smaller. You're going down a roller coaster. When you're increasing, it's like you're going up a roller coaster. The y values are getting bigger. And we're always doing that from left to right. Okay, so let's work out a couple of things here. So this one, first of all, constant would be this piece right there. And again, just look at your x values, 1, 2, 3, 4. So it looks like starting at 4, you're going to be constant. And then this graph goes on forever. You assume it goes on forever. And the thing is, always use parentheses. Do not use brackets. It's kind of hard to explain to a pre-calculus student why that is. But those endpoints are kind of neutral. They're not considered to be increasing, decreasing, or constant. So develop the habit always of using just open intervals on these. Okay, increasing, I'll highlight this in blue. These are the two regions where the graph is increasing. And again, this would be negative infinity until you get to -3. So that would be your first interval. The second one would go from an x value of 1 until you get to 4, and then put a union symbol. That's not the letter U, that's a union symbol. It means that it's joining two sets together. Okay, then the last thing would be decreasing. So decreasing would just be this region right here, and that would go from -3 to 1. Okay, so again, you're naming the intervals with x values. Okay, the next one, constant, it's never constant. This thing is never flat, it's never horizontal. So we're just going to say that it's never constant. As far as increasing goes, it would be in this region. So that would be, it looks like -1 to 1. Decreasing would be the other two regions. And again, this would be going on forever, negative infinity, until you get to -1. And then from 1, and then forever there. So you'd have negative infinity to -1, and then 1 to infinity like that. Okay, so that's how you name your intervals. Make sure that you do x values in your intervals. Make sure that you have open parentheses. Okay, I'll let you do these two problems. Go ahead and pause the video and see if you can do these okay. Okay, so you can go ahead and check your answers, see if you got everything right. Make sure that the intervals are written exactly this way. Everything's named left to right. So you never want to do this backwards, like you wouldn't say -3, -5, because that's backwards. You're always going left to right. Okay, like that. Okay, so hopefully we did that okay. Pause the video if you need to make any corrections or anything. Okay, next thing that we want to look at is what we call a local maximum and a local minimum. And this is another thing you talk about in calculus a lot. And really what it means is a local minimum just means a place in the graph where the graph changed from decreasing to increasing. So this right here is a local max, or local minimum, I'm sorry, because the graph went down, it changed directions, and went up. Same thing here, this is a local minimum, the graph changed from decreasing to increasing. So you have to have a minimum, a local minimum, you have to have something going on to the left and to the right of that point. So it has to change from decrease to increase. Local max is just the opposite thing. It means that you're going from increasing to decreasing. It's like you're up the roller coaster, you hit the high point, then you're starting to get sick as you're going down the roller coaster, okay? All right, so hopefully you don't get a stomach ache. And then same thing here, you're doing a local max, you're going up, hit the high point, and then you're screaming and going down the roller coaster like that. So just think of it that way. Okay, so we'll do a few of these problems here. So again, if you go through and look at this function, increasing, I'm going to identify the places where this function's increasing. And I'll kind of color code that. Decreasing is going to be these regions here. And this thing's never constant, so it's not flat and horizontal. So we would say we're increasing from -3 to -1, and then from 2 to 4, like that. And then decreasing is going to be, we're going to assume this goes on forever, so it would be -infinity to -3, then from -1 to 2, and then from 4 and forever, like that. Okay, constant is never on this particular problem. Okay, so just think of the roller coaster going down, going up, going down, going up, going down. Okay, now if we're looking for a local minimum, what we're looking for is a place where the graph decreases, changes directions, and increases. So right there would be a local minimum at that point, -3, -2. So that point is -3, -2. The other place where you decrease, hit a low point, and then increase is at this point. And that point looks like that is 2, -6. Now these are not intervals. These are written as points. So if I say write the minimum as a point, be sure you write the x and y value. Okay, local maximum is the opposite thing. You increase and decrease. Okay, so this would be a local max. That's at the point -1, 2. The other place is you're increasing, hit a high point and decreasing. That happens at this point, which looks like that's the 0.45. Okay, so you have 2 local minimums and 2 local maximums on this problem then. Okay. Okay, next problem, let's see, increasing, I'll just kind of do the same thing. I'll zoom on this a little bit so I can see this. So it looks like one region where you're increasing is right in here. That region there appears to be -infinity until you get to -1. Next place you increase, and this is tricky and hard to explain to a pre-calc student. You have to break this up into 2 intervals, because right at that one point right there, it's flat. So you have to say from 0 to 2. And then you have to say from 2, and this looks to me like maybe that's 3.5. I'm just estimating that. From 2 to 3.5. Now, in calculus, you learned that the slope of the tangent line at 2 is 0, and you learned that you're only increasing if the slope of the curve is positive. So, I mean, in a pre-calc class, if you combined that into the one interval, I wouldn't fuss at you. But, you know, technically, the right answer is to break that up into 2 intervals. Okay, now decreasing would be these 2 regions here. And we just name those with intervals. So this one looks like this would be from 1 to 0, or -1 to 0. And the other region looks like 3.5 to infinity. So that would go like this. Okay, and then constants never. Remember, constant, you have to have a graph where it's going like this. And even this point right there is not constant. Okay, that's just a point where the slope of the curve is 0. Okay, now if you want to do minimums and maximums, then it goes like this. This would be a local max. That point right there, which is the point -1, 0, that's a local max. This point here is a min, local min. That is the point 0, -4. This point here is not a max or a min because the graph does not change directions. And then this point right here is another local max. So that appears to be at the point 3.5 and 4. Okay, so you have one local minimum, you have one local max. Just means the direction of the graph's changing. So if this is a roller coaster, you're going up, then down, then back up to a peak, and then you go down. So think of it that way. Okay, do these two problems, pause the video, and see if you can get these figured out okay. Okay, so go ahead and check your answers and see if you're on the right track. Number one, you had, and I just estimated these numbers, so I mean, you didn't have to have exactly what I had here. I said negative 1.8 is kind of where I was thinking that minimum is. If you put negative 2, that's okay. You're just estimating that anyway, so that's okay. This one has two local minimums, this point here and that point there, and it has one local maximum. Okay, the next one, let's see, this one has one local maximum and it has one local minimum. Those are the only two places where the graph changes directions. You increase, decrease, and then at the minimum you're changing from decrease to increase. Now, this interval on increasing should really be written as two intervals. The technical reason for that is the slope of the curve is a vertical line and the slope is undefined. Again, in a pre-calc class, if you did this like this and just said 1 to 5, I'd be okay. Now, this does not go to infinity. This graph right here stops. So this is not a graph that's going on in both directions to negative infinity, infinity. So you needed to catch that on that point too. That's because there's a solid dot. Whereas in the previous problem, you have arrows. Okay, so pause the video if you need to make any corrections. Okay, so one last topic, we're going to talk about absolute extrema, another topic you talk about in a calculus class. And all this means is like an absolute max is just the biggest y value that the graph ever achieves. So it's like the highest point on the graph. And then an absolute minimum is the smallest y value. So it's the lowest point on the graph. And you can have more than one absolute max. You could have the same value maybe on several places on the graph. So typically, we usually give the y value for an absolute extrema, or you can give it as a point. Okay, so down at the bottom here, this one we would say it has an absolute minimum, and that's occurring at when x is equal to 0. It does not have an absolute max because the graph's y values go to infinity. They get infinitely bigger. Okay, the next problem, notice you have solid dots on the end, so you do have an absolute min there, and you do have an absolute max there. Okay, we say absolute max of 4, we give the y value, and then we tell what the x value is. That's the standard way of doing that. You say absolute min of 0 because that's the y value. Okay, or you could write a point. You could also just say at the point 2, 4, you have an absolute max. At the point 0, 0, you have an absolute min. Okay, on the next page, you do have an absolute max because that's a solid dot. So we would say absolute max of 4 when x is 2. Okay, now, this one can be a little tricky, but you have an open bubble. That means that the graph's undefined. So that means y is never going to be 0. Y is going to be infinitely close to 0. So y could be something like 0.000001, but it could get even smaller than that. You could just keep adding zeros before the 1, but you will never reach a definitive y value. You're getting close to 0, but you're never reaching it. That's why there's no absolute min. So if there's an open bubble, That's not a point, and since that's not a point on a graph, that cannot be a min or a max. Same thing occurs on the next example. You have open bubbles, so you're never going to reach that point. Okay? Okay, so let's do a couple of examples together to kind of finish this up. So this graph we have, this would be your absolute max. And since I'm not giving you y values, I'm just going to say, okay, that absolute max occurs at x equals b. The absolute min is there. That's an absolute min. So that occurs at x equals c2. Again, that's the lowest place on the graph. That's the highest place on the graph. Okay, now these things right here, like this point here, would be a local maximum. A local max is where the graph changes from increasing to decreasing. This point right here would also be a local minimum because the graph changes from decrease to increase. This point right here is nothing. So the thing about this is an end point, and this is pretty important on this. If you have an end point will never be an absolute extreme value. It'll never be an absolute max or min. But an interior point can be a local min or a maximum. Okay, this point right here, there's your absolute max. That occurs at x equals c. Absolute min, there isn't one. Okay, because that's an open bubble. That graph will never reach that y value. It'll just get infinitely close to it. Okay, next problem. There's your local min. That's your absolute min right there. So that's the lowest value of y, the lowest point on the graph. Since that's open, there is no highest point on this graph, so there is not an absolute max. Okay, next problem. That's your absolute max right there. That is a solid dot. That is the highest value of y that the graph ever reaches. So we'll say we have that absolute max at x equals a. Absolute min is the lowest place on the graph, so that is equal to x equals c. Okay, so be careful when you do these, but pay attention to whether there's an open bubble, meaning you're undefined at that point, versus a solid. Okay, move to the next page, and I'll have you wrap this up with these two problems. So I'm going to go ahead and pause. Okay, so if you go ahead and just kind of check your answers, see if you did this okay. See, this one has two absolute maximums because they have the same y value. Now, I just went ahead and wrote them as points. You could also just say maximum of 16 when x equals either plus or minus 2. Absolute minimum is this point, 3, negative 10, or you could also just say negative 2, negative 10 when x equals 3. Now, this thing does have a local minimum. A local minimum means the graph is going down, hits a low point, and going up. So that is a local minimum. This point here is not local. Okay, and then local maximums means the graph changes from increasing to decreasing. So these 2 points here are local maximums, and at the same time they're absolute maximums. So an absolute minimum and an absolute max can also be a local min or max. But an endpoint, like I said, cannot be a local max or min. Endpoints can only be absolute maxes or mins. Okay, problem 2, there is no absolute max because that's open. Absolute min is this point right here, 4, 1. That's closed. And then as far as local min, the graph has to change from increase to decrease. So that's a local min. In order to have a local max, the graph has to change from increase to decrease. That happens 2 times. So those are your local max and min. Okay, that'll wrap up this video. Pretty short video. Pretty straightforward information. All right, hope this helps.